Welcome to RISE Learning Machines seminars. And now I see we have video of Joel as well. That's great. I am Olof Mogren, and I'm a researcher on foundational and applied machine learning at RISE. RISE is Sweden's public research institute, and this is our weekly seminar on AI and machine learning. This meeting will be recorded, and if anyone wants to be removed from this, let us know. Do check out the collection of previous recordings on our YouTube channel. I have the pleasure to introduce to you today Joel Oskarsson, who is a PhD candidate at Linköping University, working on probabilistic machine learning and applying these methods on Earth system modeling. And the topic today is frontiers in machine learning for weather forecasting. With this said, I will stop my sharing and hand over the word to you, Joel.
Thank you. So I should start my sharing. Now you should be able to see the slides well, right?
Yes.
Okay,
Perfect.
great. Yeah, so thanks for the introduction. So as Olof said, this is a talk about the frontiers in machine learning for weather forecasting. Gonna cover a few. This one to work? Yes. I'm gonna cover a few different topics in this presentation. The rough outline is that I'll start by giving a bit of context and talk about the kind of revolution we've seen in machine learning weather prediction. And from here on, I will just abbreviate this as MLWP because I will mention it quite a lot. A little bit on the background and what has kind of enabled machine learning to become really important for weather forecasting today. And then I'll be focusing much of this around the very current research directions. So where sort of past initial works, where does this research area stand right now and what is possible? Much of what I'll talk about will be related to graph-based MLWP, so utilizing graph neural networks. So I'm also going to give a bit of an overview of how that kind of framework works. So you're able to follow those things later. And then I'm going to dive into a few of these research frontiers and a few where I have done work, which are regional models and also probabilistic modeling. And I can see, yeah, so I can't see the chat right now, but maybe if there's questions, please just interrupt me and then I can clarify different things. And then I hope in the end we should have some more time for more in-depth questions as well. Okay. Yes, so what's the deal with MLWP then? Why is this so interesting and maybe why right now? So I think one quite straightforward motivation for why this is worth paying attention to is just to look at a plot like the one to the left here. This is the root mean squared error for 2-meter temperature of forecasts up to 10 days. So the top line in this plot, the solid blue one, that's the IFS HRES model, which is a kind of state-of-the-art physics-based weather forecasting system. And then we see the two lines under it, those are machine learning models. So we are now at the point that the machine learning models are competitive and outperforming traditional physics-based models for weather forecasting. And not just are they outperforming them on metrics like this, but they also run a lot faster than traditional physics-based systems. So the machine learning models can run on sort of a single GPU in a few seconds and produce a forecast, which can be compared then to physics-based models that run on these huge CPU clusters, and they often take quite some time to create one forecast. So Science magazine, for example, they named AI weather forecasting as one of these great scientific achievements in 2023. So this is really considered something that is changing the playing field. And I like this quote here, that in our view, we are currently placed at an exciting moment in weather forecasting history due to the machine learning. And this is from the European Center for Medium Range Weather Forecasting, the ECMWF, who are quite the authority in this area. And this developments sort of have really shown also in terms of the models that's been released. So I would say from the start of 2022 is when we saw kind of the first models that were really competitive with traditional physics-based models. And then there's just been this constant flow of new models being released. And sort of at the start of this year, I stopped updating this timeline because there's just too many things coming out with interesting ideas. And a lot of these developments have also been fueled by the involvement of big tech companies. So if you consider the models listed here, I would say that almost all of them have some kind of involvement from these big tech firms who have been very, very interested in developing their own weather forecasting systems and pushing these developments forward. But we can also sort of ask, what was it that enabled this progress right now? And what kind of enabled this MLWP revolution? So I would say that as is often the case when machine learning is very useful for some kind of area, one of the main reasons for that being possible is the existence of data. So one or multiple really good data sets. And for weather forecasting, I would say that data set is the ERA5 data set. So this is a global reanalysis data by ECMWF, this center. So a reanalysis data set pretty much means that it's the best estimate we have of the atmosphere of Earth for a long time span. So you take all of the observations that you have of the atmosphere, and then you try to estimate the state for a long time. And then you can use this then to train machine learning models on it. In terms of the models themselves and the machine learning methods, of course, it's been deep learning. That's the thing that's driving this. But what's a bit interesting here is that there's not one kind of model architecture that's the one to use in weather forecasting. Actually, there's been a few different that's been successful here. So graph neural networks, transformers, and also neural operators have all been used to build very well-functioning weather forecasting models. And then I guess another key component here is, of course, having lots of GPUs to train these models on. So while they might be able to produce forecasts very cheaply, you still need quite some computing power to actually train these models. And this also then connects back maybe to the fact that you have these big tech companies pushing this development. So we think a bit also about this as a research area, the machine learning, weather prediction research. What is the kind of goal and what's been the goal in these papers? If we look at the first models here, the focus has really been on outperforming physical models. So showing in some ways that machine learning models can forecast the weather as accurate as traditional physics models. This, I would say, at this point is kind of proven that this is possible, at least by these kind of standard metrics like RMSE. So it's not something that one has to prove in that way anymore. And now I think we're instead seeing that the research area is maturing a bit, and we're starting to think about the different kind of properties that these models have, and the different ways we can, sort of new and interesting ways that we can use these kind of models. So I've listed here a number of research directions that I think are really interesting and when we start to see first works going into. So of course, things like the neural network architectures themselves, but also forecasting longer times, the sub-seasonal and seasonal timescales, pushing things to higher resolutions, both in space and in time. Regional forecasting is something I will touch on today. Interactions with the ocean and the ice, for example, and forecast uncertainty being ever so important. Including observations in ways to make the forecasts higher accuracy, something that's also being worked a lot on. Downscaling or super resolution is maybe the machine learning terminology, as well as data simulation is something where machine learning plays a big role. So for estimating the initial conditions that we start the forecasts from. And I'm going to talk about a few of these directions here today that we have done work in. So a bit about neural network architectures, but really focusing on regional forecasts and the forecasting uncertainty. But before going into these kinds of research frontiers, I thought I would also lay a little bit of the groundwork on how we can think of machine learning weather prediction and define a little bit of notation that I will use here as well. So consider xt here as kind of the weather state, the state of the atmosphere at time step t. So this then includes a number of different variables that we're interested in modeling. So it can be wind, temperature, humidity, and so on. And often also at multiple vertical levels throughout the atmosphere. And we consider xt containing all of these variables for all of the spatial locations that we're modeling as well. So typically we work with gridded data. So we have some kind of grid, and then we model these different variables in each of the grid cells. So apart from the state itself, we often have some kind of forcing as well. So some known input that we can give to the model that then we don't have to predict, but that we know a priori and can inform the model to make a better prediction. So for example, the time of day is something that can be useful to feed to the forecasting model. And then we assume that there exists some true kind of dynamics model, F here, mapping from previous states to the next. And the goal of machine learning here is really to approximate this with a model F hat that we then can learn from data. And once we have such an F hat, then we have also some initial state to start the forecast from. We can apply this to get the next state, and feed this back into the model again, and in that way roll out a forecast of whatever length we're interested in. And this is in many ways similar to traditional physics-based models, this kind of iterative rollouts of forecasts. What is different here, though, is that we actually need to learn this F hat. So we need to train the model on some data set of weather state trajectories. And there's a couple alternatives here. So we can train such models directly on forecast data, so a data set of saved forecasts from some existing model. And that's useful if you want to build like a fast surrogate model for an existing forecasting system. So then will benefit the fact that the machine learning models run very, very quickly. But we can then also train our models on reanalysis data. So these data sets like ERA5, for example, and that's what then enables us to surpass the existing physics-based models and get even higher accuracy. So that's the sort of general framework. And now I'm going to talk specifically about the graph-based MLWP, where you use graph neural networks. And the key idea of the graph-based approach is that you want to construct a mesh graph covering your forecasting area. So you construct this additional graph. If it's a global forecasting model, then this graph should cover the whole globe. Or if it's just some limited area, then that graph will just have to cover that area. And the point of creating this graph is that we typically have data at many spatial locations, a very high spatial resolution. So working with a model directly on the data grid is not very efficient. So we want to instead, in some way, encode our data to this mesh graph and then perform the computations on the mesh graph instead. And that then becomes much more efficient. So the way we use this graph to make a prediction, to make a forecast one time step ahead, is using a framework called encode, process, decode. So the idea is that you take your input, your previous time steps that sits at this grid, you encode this up to the mesh graph, then you perform a number of processing steps on this mesh graph. Finally, you decode back down to the grid again. And then that's your prediction for one time step ahead. And you can do this many times over in order to then roll out a full forecast. And I didn't say anything sort of what happens in each of these steps now. It's kind of abstract. And that's because each of these steps are then parameterized as graph neural networks or GNNs. So really when training these models, we learn how the encoding should be done and what should actually happen in each of these processing steps. So I'm guessing some might be familiar with graph neural networks, but I still like to include also this slide, which is a brief introduction to GNNs to get a better idea of what it actually means that we apply GNN layers. So kind of the core idea of graph neural networks is that you have vector representations of graphs. So you have vector representations of nodes. So in this example, I have a graph with 4 nodes, and you have a vector v associated with each of them. And then you have vector representations also of the edges. So that's the e vectors in this case. And when we apply a graph neural network layer, that's in some way updating these different representations. And the way this update process works is that you first compute messages, so 1 message per edge, and then you take in the edge vector as well as the node vectors representing the endpoint nodes. You feed this all through some little neural network construction, and then you output the message e tilde corresponding to that edge. You use this message, then feed it back through some other neural network, and that gives you the updated edge vector for that edge. And then you also use these messages to update the node representations. So for a node R here, we consider all of the incoming edges. And then we aggregate the messages for those edges in some way. So typically you just sum these up. And then you feed the result of that through some other neural network, and that gives you the updated node representation VR in this case. And then you do all of these steps completely in parallel for all of the nodes and edges in the graph. And that's how this becomes efficient. And you can stack multiple graph neural network layers after each other. And then you're learning all of these different neural network components inside of them. And that way you get quite flexible transformations of graph representations. And this is then what actually happens in each of these steps, in the encode step, in each of the processing steps in the graph-based framework. So I hope that gives at least a rough idea about how these graph-based methods work. So now I'm gonna give some examples also of how these graph methods are used and talk about these different frontiers. The first one being regional MLWP models. So the motivation for work in regional modeling here is to a large extent that when I listed all of these papers and all these models initially, those works have been largely focused on global weather forecasting. So that's really been seen as this kind of application that you want to show that your model works great for, which makes sense because that's a very important problem. But also quite important is to be able to run models at very, very high resolutions for a specific area. And this is kind of where regional MLWP comes in. So the idea here is to try to take these developments from global models and try to apply them also to these high resolution regional models. And I'd say there's mainly 2 approaches to this in the literature, or that I find the most interesting at least. So the first one is what's called the stretch grid model. So the idea here is that you still run a global model. So you're still forecasting and simulating the weather for the whole Earth. But then you tailor this model in such a way that you focus more on a specific region that you really care about. So you might have an additional data set for this region that you use for training, and you increase the spatial resolution for the region you're interested in. The other approach, and this is where our work comes in, is the limited area model approach, or LAM. This is a bit more similar to how traditional physics-based regional models work, where you're only forecasting for that one specific region that you're interested in, and then you condition that regional forecast on information from the surrounding area. So you're imposing boundary conditions on this limited area forecast. I'm gonna cover now this limited area approach in a bit more detail and going over sort of the research project that we have done with these kinds of models. So when working on this, we've been collaborating with SMHI, and then we've been working with a data set from this Met-Co-op ensemble prediction system, the MEPS system, which is the operational weather forecasting system being run in Sweden, Finland, and Norway, and some other states jointly. So this is one of the physics-based limited area forecasting systems. And the data we're working with here is on a 10-kilometer resolution. So that's a 238 times 268 grid. And the idea here really is to try to emulate this map system with some fast deep learning model. So we're not necessarily setting out here to try to outperform the map system, but really just to build a very quick emulator. And the reason for this is that the data set that we're working with here is forecasts. So we have 6,000 forecasts from this map system. And then we're forecasting 19 time steps ahead with 3-hour steps, so up to about 57 hours. Yeah. And then we're forecasting a number of different variables. It's a quite long list. I think in total there's 18 of them. We consider a number of forcing inputs here as well. So within the region, we use forcing such as the land-water mask in every grid cell. And then we have this additional forcing that is the boundary conditions for the region. So this is something you would typically then take from another forecast. So if you would have run another global model, for example, or if you get it from some other center, then you can impose that as boundary conditions. In experiments here, we actually just take these boundary conditions from the MEPS forecast data itself, because that allows us to easily experiment with this, but you could then replace them with what you would get from a global model. So a consideration now with applying MLWP to this, and in particular, we're interested in applying this graph-based framework that's been very successful, is that we need to construct this mesh graph. So we can't just build a mesh around the Earth anymore, but we need to do it for the area we're interested in. So we tried a few different approaches here. First, building this kind of simple single resolution mesh where you just lay out nodes in regular rows and columns and you connect them up to their neighbors. So a bit more of a refined approach is to build what's called a multi-scale mesh. This is similar to the global GraphCast model. And the idea here is that you don't just connect these nodes to their neighbors, but you also include some longer edges in this graph and longer connections that can then transport information longer spatial distances, and you can model spatial processes happening on different scales. The multi-scale mesh, however, has some drawbacks we found, at least in this kind of setting. And that's because it's a very heterogeneous graph. So you have some nodes with lots of neighbors and then some nodes with very few. And when you connect this back to the grid for actually making the prediction, that can cause issues and artifacts. So motivated by this, we also extended this further and built this kind of hierarchical mesh graph as well. So here you have a much more uniform structure at every level of this hierarchy. You still have some longer edges and shorter edges. And then we added in also additional edges in between the levels in this hierarchy. And then with this hierarchical mesh, we also needed to redefine a little bit how this encode process decode steps actually work. So here we're doing kind of sequential passes up and down through this hierarchy in order to produce a prediction. Okay, so then we applied, or we implemented all of this and tested out the hierarchical model on the MEPS data. And here are some example forecasts. So you have the ground truth forecast from the MEPS system to the left, and then the prediction from the machine learning surrogate model to the right. And you see this kind of boundary around each of the forecasts. That's the conditioning information from the outside. So what we can see in this is that the machine learning model is quite nicely able to learn most of the large scale patterns and simulate this accurately. But especially as time goes on here, it's losing a lot of the finer details in the forecast. And this has been a sort of problem encountered by multiple machine learning models, and relates a little bit to how we kind of train these models, especially when we train deterministic models. So I'll return a little bit to this when talking about the probabilistic models later as well. There's this kind of smoothing effect that we, to some extent, should expect here as well. So that's some examples of how we can build regional models. And now I want to move on and discuss forecast uncertainty here in probabilistic modeling. So this is something I've worked in most recently, and I think is very exciting. So this is what I would say really one of the key questions in this research area now, how to do this in good ways. And we see all these sort of initial ideas really popping up, I mean, any other day right now. So when we think of weather forecasting as a probabilistic problem, there's two main sources of uncertainty. One is uncertainty in the initial conditions that we start the forecast from. And the other one is uncertainty in the mapping for the next time step, so in the dynamics going forward. What I'll talk about here mostly is this second type of uncertainty. So not so much focusing on if we have inaccurate initial conditions, but rather how we can capture uncertainty in what actually happens as we're moving forward in time. So what we would really want for quantifying forecast uncertainty is to capture the full distribution of possible future weather states. So all of this distribution over x1 to t, conditioned on some initial conditions and also on whatever forcing we're feeding the model in with. And this is a really high dimensional distribution. So the feasible way to work with this is to draw samples from it. And that's what then leads us to ensemble forecasting, where we roll out a number of possible future trajectories as samples from this distribution. So we can think a bit more about how do we actually view this distribution of future weather. So typically we make these kinds of assumptions that we can decompose this distribution over time, and we only let every state depend on the previous two states. This is a second order Markov assumption that is typically done in the machine learning models. So then the question becomes, how do we model this distribution for the next state given the two previous ones? And when we think of the deterministic models, we train these with some kind of mean squared error loss function always. And this implicitly means that we're assuming this distribution to be Gaussian, and we only model the mean of this distribution. That's what our neural network outputs. And we're also assuming a completely diagonal covariance matrix for this. And it's not maybe so strange that this mean of the distribution is not necessarily what we're interested in. So this mean in itself might not be a reasonable weather state. This mean is likely quite smooth, as we saw earlier, because we're averaging over many possible small details. So whenever we cannot predict those details accurately, the mean will be some kind of average of all of the possible variations. So this might not be a great model, especially when we're starting to think of longer times. But we actually have lots of great tools in machine learning for modeling distributions. That's in many ways all what machine learning is about, right? So deep probabilistic models in particular have really proven to be useful all over the place, and we can build them quite well. So kind of the natural idea here is to specify this distribution as some kind of conditional generative model. And then the question is, which model should we use here? So I think there's two directions that we've seen in the literature for specifying this distribution as deep generative models, or at least two that are, that most works go in, the few works that exist, I should say. So one approach is latent variable models. So you can think of these kind of as dynamic variational autoencoders that try to model this distribution using some latent random variable. really early work in this direction is the SWIN VRNN model. It uses a SWIN transformer. And then in our work, we've introduced a model called Graph EFM that combines this latent variable model setup with the graph-based weather forecasting framework. Another choice for this distribution is to model it as a diffusion model. So diffusion models have been successful for all kinds of things, I guess a bit more recent than latent variable models. So the GenCast model is one example of this coming from Google DeepMind. And then we've also done some work on using diffusion models for this, and a model called ARCI. And now I'm gonna zoom in a bit on these two that we have worked on here, both as kind of examples of models in these families, but also to show a little bit about what kind of properties one can build into these models. So I'm starting here with the Graph EFM model, and that comes from this paper called Probabilistic Weather Forecasting with Hierarchical Graph Neural Networks. Right. So for this, we're building on this latent variable formulation. So it means that we're specifying this distribution here over xt using some latent random variable ZT. So we have one of these for every time step. And the idea is that this ZT should in some way capture the uncertainty in the single time step prediction. So we specify this distribution as this kind of integral where we're marginalizing over ZT. So there's two parts here. The first one is what I call a latent map that maps from the things we're conditioning on to the distribution over ZT. And this should then capture in what ways we are uncertain about this prediction for the next time step. Apart from the latent map, we have what I call the predictor part of this that conditioned on one specific realization of ZT, then produces the actual prediction xt, so the actual forecast for the next time step. And we will realize both of these two parts as neural networks then. And specifically, we will here use the graph neural networks and then combine this with this graph-based framework. And we're actually going to bring back the hierarchical graph from earlier here again and associate these different quantities with different parts of this graph hierarchy. So the conditioning information, the previous states, and the forcing that comes in from the grid from the bottom of this hierarchy. But then this latent variable ZT we associate with the top level of the hierarchy. So different dimensions of ZT are associated with different nodes at the top level, meaning that the latent variable is lower dimensional, and it also has a kind of spatial structure to it. And I showed this is a limited area graph here, but we've actually worked with this method both in the limited area setting and for global forecasting. And most of my examples here are for global forecasting. So when we put this kind of probabilistic framework then together with the deep learning framework of graph neural networks, we get this kind of model setup that we call Graph EFM, graph-based ensemble forecasting model. And see, I think you can see my cursor. So the idea here is that we take the conditioning input, states at previous time step. We feed that through this hierarchy of graph neural network layers, and then that specifies the distribution over ZT. Similarly, we feed it up in the predictor part of the model, up to the highest level of the hierarchy. And here we sample one specific value of ZT. Oops. I will trying to go back to the previous slide. There we go. Then we sample one specific value for ZT, and then we combine this at the top level of the hierarchy in some way. And then we're propagating this again back down the hierarchy. And as we're doing that, the randomness from this sample is kind of spreading out over the forecasting area. And finally producing this prediction xt in the end. So you can note here also that if we wouldn't sample this ZT, then this would be a completely deterministic model. So we could construct the model also like that, and we call that setup graph FM in this case. So another thing to note about, and this is really general for the latent variable models here, is that sampling the forecast for one time step ahead is quite efficient. So we really just need to do one forward pass through the whole model. And then, of course, we need to do this at every time step when we're rolling out a longer forecast. But we should contrast this to the diffusion models that typically, where sampling in those typically involves solving some ODE. And that in terms requires many forward passes through the neural network. So it's often an order of magnitude slower than what can be done in the latent variable models.
Question you
now, yeah.
The prediction part of the network looks very similar to a UNet. Do you have some comments on that? Is it a UNet or is it just how it?
Yeah, I'd say that's a very accurate. It's very much inspired by that. So it's a sort of graph version of a UNet, I would say. There are some small differences, but it's really that idea, taking in these kind of multiple spatial scales in the same way that you have in a UNet. Yeah.
Thanks.
And it's actually in the limited area case where you have this kind of much more regular layout, then it's very close to a UNet. Just that you have the actual graph neural network layer specified in a bit of a different way. Yeah. Yes, so some results on how this can work then. So this is for global forecasting, where we train on this ERA5 dataset here on a 1.5 degree grid, forecasting 83 different variables up to 10 days with 6-hour time steps. And of course, the models perform a bit different on all of these 83 different variables, but I included here specific humidity that I think is fairly representative. And there's a lot of baselines in these plots, but maybe most interesting is the graph EFM model is the solid blue line. And then we can compare this with a much more naive or simple approach to create an ensemble forecast, which is to combine a deterministic graphcast model with stochastic weight averaging for this graphcast.swa. Yes. So we can see that that one achieves a lower root mean squared error in the plot to the left. But then we consider a probabilistic metric like the CRPS, then we see that actually it doesn't capture the distribution very well. So then the graph EFM model has a much lower score. And for considering also, so I mean, we want these uncertainties to be useful and to be meaningful. And one common way to assess that with ensemble forecasts is to look at the spread skill ratio. So we want this ratio to be equal to 1. And when we compare the models to the plot in the plot to the right here, then there's quite a big difference that the graph EFM model really flattens out at 1, whereas these other baselines don't reach. Well, they're not really close to it at all in this case. So it means that at least the first check for these uncertainties, they seem to be meaningful and could be useful to us. And then we should also, of course, look at some example forecasts. So in these kind of animations, we have the ground truth at the top left. We have the ensemble mean in the center at the top. And then we have the ensemble standard deviation, finally, the right in the top row. So the standard deviation then tells us in some sense in what way we are uncertain. And the bottom row are then 3 different ensemble members sampled from the model. So when looking at these ensemble members, we can see that at short lead times, they are looking very much the same, but then as time progresses, there's different kinds of weather patterns that start to appear in the different members, and this is what we want. It tells us that, okay, we can't really say for sure what's going on in certain regions, and then that's accurately represented by diversity in ensemble members. Okay, so I have a little bit of time here to also talk about the diffusion model. So I will give a very short presentation also about this work, which is continuous ensemble weather forecasting with diffusion models. So this is some research headed by Martin Andrea in our group, where we're looking at using diffusion models instead of these latent variable models for ensemble forecasting. So I'm not going to give a sort of in-depth introduction to diffusion models, but the short idea is that you're sampling some Gaussian noise, and then you have some neural network that removes a bit of this noise, and then you apply this many times over, and eventually you end up with a sample from your data set, or something that resembles what's in your data set. And this kind of denoising process can also be reformulated as a deterministic ODE that you then solve with a numerical ODE solver. So for weather forecasting, we want to learn a diffusion model for this distribution over XT. And the way we do that is to set up a training objective to learn this kind of denoising network conditioned on the previous time step and the conditioning information in this distribution. So we're asking the denoising network to denoise a noisy state XT conditioned on information about what the previous the state at the previous time steps. And if we learn such a model, that's something we can then use to sample from, and we can do this auto-regressively, as we've seen before, to roll out forecasts up to, let's say, 10 days ahead or so. This auto-regressive forecasting here does, however, have some issues. So first of all, this is a very sequential process that we cannot parallelize. And especially for the diffusion models, this becomes sequential as the sampling in itself at every time step is also sequential. And also taking many steps like this, there's also error accumulation going on. So if you're taking very short time steps, then your error will start to accumulate very quickly, and you will start to get quite poor performance for later lead times. So in this work, we wanted to try to remedy these things. And there's a few ideas here going into this. So one is to condition the sampling itself and also the model training on the lead time we're interested in. So doing direct forecasting. So here give the model, we tell it, okay, I want the forecast for 1 day ahead, and you produce a sample for that, or you want 3 days ahead, you produce a sample for that. This is great, and you can learn a model like this, but it also means that you might end up with lots of samples at one time point and then lots of samples at the next time point, but no sort of relation between them, no temporal coherency. But this can then be fixed, quite simple, by just fixing this random noise that you use to start sampling with your diffusion model. Or alternatively, and this actually has some benefits, to specify this random noise as a stochastic process over the lead time. So this kind of approach works, but it also has some limitations on how far you can push it. So you can't, for example, give initial conditions to the model and say, okay, I want to forecast 10 days in the future. It will be a very hard problem for the model to solve, producing a sample at that time. What you can do, however, is to at least do this for shorter lead times and then combine this with the autoregressive approach. So this is what we've done in this method that we call autoregressive rollouts with continuous interpolation, or ARCI. So you can take autoregressive steps on, say, 24 hours, but then you can do this kind of continuous interpolation for forecasts at lead times in between those 24-hour steps. And we experiment with this also on ERA 5, but this time at 5 degrees resolution. And I think these plots are quite interesting. So if you look, these are the same metrics as before. And if you look at the blue line here, that's an autoregressive diffusion model taking 1 hour time steps. So that gives you high temporal resolution, but as you can see, the error of that model grows really, really quickly. And we can compare this then to an autoregressive model like the pink line here that takes 24-hour time steps, achieves a lot lower error because you don't have this error accumulation. With this ARCI method, we can actually get forecasts as 1 hour resolution, but keeping to the same accuracy as the 24-hour autoregressive model. So in some sense, getting both of the best of both worlds here. So both the error of the 24-hour model, but still a very high temporal resolution. So now I've been talking a bit about these probabilistic models for a while, so I think I should summarize what this has been about. So from the beginning here, I think I set out that machine learning is fundamentally changing weather forecasting. So the way it's being done today, and I think we'll see this even more so as more of these methods start to become operationalized, different centers and in different ways. There's now a lot of open and quite exciting research directions. So the first kind of model showed that machine learning is competitive, but now the question is kind of what properties can we give these models and in what ways can we really use them? So I've talked a bit about two research directions that are being explored. So one being these regional MLWP models, where I presented our work on limited area models. And then in the end here, more about probabilistic weather forecasting and two different options for this being latent variable models and diffusion models. So in the end here, I'd like to say thanks to all of my great collaborators on these works. I listed the different papers I've been talking about here as well, and there's a link to the code also. So that's the code for the limited area models and the graph EFM model as well in this Neural Lam GitHub repository. So thank you very much.
Thank you, Joel. I think while everybody is thinking of what questions they're going to ask, I'll start off with a couple questions. You mentioned the ERA5 data set and that's sort of the standard data set that's being used in these settings. For how long is that data set going to suffice, or are there any wish list of what should be needed to take things to a next step? Or is this data set everything that we need?
I'd say it's definitely not what we need. I think there's probably not a consensus, but there's at least a lot of thoughts that what is actually keeping machine learning models from getting even better is what is sort of the limiting factor is ERA5 as a data set. And that's maybe one reason why we see many different kinds of architectures working well here is that it's not some sort of machine learning methodology you need to improve here, but rather you sort of reach the best you can do with this data. I mean, there's probably some more performance to squeeze out, but it's one of the main limiting factors. They are preparing, sort of in the process, I think, starting out to prepare an ERA6 data set, and there's a lot of consideration on machine learning for that. I think I am more excited about developments to move past the use of reanalysis data sets than the idea of a lot of work being put into one reanalysis data set. Because in some sense, when you create the reanalysis data set, you're taking all of your observations and then you're, in some sense, encoding these into this data set so it's in a useful format. And then you're training a machine learning model on that. So another current direction here, right, is to use these observations more directly. So rather than to create an reanalysis data set from them to see, okay, can we build machine learning models that directly ingest all of these different observations from satellites, weather stations, and so on, and then produce very accurate forecasts from those.
All right, thanks. So we have a question in the chat from Laura. Laura, do you want to read your question? Otherwise, I can start. I can try to read it. Yeah. So on a global synoptic models, the changes on altitudes are not considered. Those then start being modeled in mesoscale models, especially in the gamma 2 to 20 kilometer grids. I wonder if your neural network regional forecast was degrading over time. Is the orology taken into consideration in the regional models that you presented?
So let's see. I will do my best to answer this, given I'm not a meteorologist. So I mean, what do you say? The surface height is taken into consideration as an input to the models, the orography, if that is sort of what you're going for here. And then you have the different variables are at different vertical levels in the atmosphere. So in the limited area models I presented here, it's actually a bit of a mishmash, the kind of vertical levels that are being modeled. So it's not an optimal setup, I would say. So some of them are at very specific pressure levels, and some of them are just at kind of the surface level defined in a different way. But in general, we take into account the orography, so things like mountains and so on. So the model can adapt to that. Then, in what way the model uses that as a useful information, that's something, that is hard to really analyze. But I think in general, we see that it. So for example, it's when other things become a bit blurry, it's still taking into consideration, for example, where the mountains are located. So it seems to be making quite heavy use of that information. I hope that is in some way useful as an answer.
Right, great. So we have a question from Sepide.
Hello, thank you for a very interesting talk and also very educational. I learned a lot. And I have a question that, for example, if you want to model the region, a specific region, do you recommend a stretch grid models or limited area models? Which one do you think would perform better? And I have a second question, but maybe this goes first, and then I can ask the next.
Yeah, exactly. Yeah, so it's a bit hard to say because I don't think we have a direct comparison. It depends a little bit on what kind of capabilities you would want, and what kind of setup you would sort of envision yourself running this at, I guess. So do you envision yourself getting initial conditions for the full Earth and then sort of starting out from that? Do you envision yourself having a global forecast available or running that as well? So we don't have a comparison on this. I think there is work sort of ongoing to try to do a more of a direct comparison. I find the limited area setup a bit simpler in the sense that you're only focusing on that one region you're at. So that would in general require less GPU memory, for example, if you want to go to very high resolutions there. But I can also see that if you have the capabilities and you want to just learn a really good global model at the same time as a very good regional model, and you want to throw sort of lots of data at it, then I could definitely see that the stretch grid approach could be more useful. So it's also a bit of a non-answer here, but of course I'm also a bit biased in having worked with the limited area models now. But yeah, that's probably what I would say.
My next question would be, you have the codes in the GitHub, and I suppose they are for a particular region that you have data set for. How do you think, how easy would it be to retrain those models or like fine tune them for a new area?
Yeah, so we're actually, so this repository, NeuralLam, we're trying to now adapt it. So
I guess it puts a little bit of a lid on the discussion if we should continue it without you. But I'm sure he is aware of his connection issues. Perhaps I can sort of chip in some general information before we continue, and then if he reconnects, then we'll continue the discussion. I will add the announcement that next week we have a canceled seminar because of a cancellation from the speaker. So the next seminar is in 2 weeks, and that will be Alp Kutschukobir, who's a professor at Columbia University. He's chief scientist at Ferro Labs, and he is at the core team of climate change AI. And he works on statistical and causal machine learning for climate. And along those lines, we're also announcing or starting a a Nordic network for working on AI for climate change. We call it Climate Change AI Nordics. And the web address is ccain.cc. Alexis has put the link in the chat. So anybody who wants to connect with this network, please go in and join. We're also organizing a workshop this spring in Gothenburg. Alexis put the link to the workshop as well in the chat. So please do check it out. We'll add more information as we go. I think Joel has reconnected.
Yes, sorry about that.
Yeah, no worries.
Things having some Zoom issues with it.
Yeah, well, you're back. Great. So I guess we can repeat the question that we were discussing. And
yeah, my question was about the fine tuning of the models for the new location, because like in some of the applications we are working at, we are interested in modeling forecasting the weather, but in a particular location. And I was wondering do you think that would be feasible?
So one particular location, as in sort of a
Yeah.
grid, or on one very specific point?
It's a very specific point in the map, like area in the map.
Yeah, there's this kind of fun idea that I have been playing around with, or I'm playing around with in my head, not actually testing out, which is that the graph-based models, you can really put these kinds of nodes anywhere. So you could take a model like this and then you place the node exactly where you want your forecast, and then you connect it up. And I think you would still need to fine tune things a bit, because I'm not sure if it would work like immediately.
Maybe you're froze again, I don't know. But then we need a data per any node in a graph. Am I right?
Yes, you would need data for that specific node then to fine tune it.
Thank you.
But you could also try out what would happen, sort of, because the model should in some sense be able to generalize also to new locations. And there are some, like the neural operator models, for example, might be a bit better at this as well. So that might also be something to look into.
Thank you.
Right, I think we have a question from Ashwin as well.
Right. So great work. I've been following your work for a while. So one question I had, like, once given that this kind of machine learning focus models surrogates are operationalized, when you are faced with changing weather patterns and maybe changing climate as such, how would you envision the workflow would be to retrain the model for the same setup?
Yeah, so I think my video has frozen, but I hear you, so I can just answer anyhow. Yeah, so the sort of changing climate is of course a consideration. In machine learning, we're assuming that the distributions of the data sort of stays the same. So I think that can be a problem. But there's also a question a bit about time spans here. So things luckily do not change that quickly in terms of the distributional shift of climate. And I think there will definitely be a point where you will need to retrain these models, but I'm not sure if the climate shift will be the first sort of motivation for this, rather than a sort of new methods and better data being available in some other way. So I think if you're running this like in a very much an operational setting, you would probably have some kind of setup to refine tune these models on a, I don't know, yearly or even more often basis.
Well, I have one more short question, like, if you don't mind. So in operational setting, you have forecast, and then you have the analysis to ground it based on observations. And the analysis part is, of course, usually done by a physical model. Do you think that the analysis part can also be substituted with the machine learning part? Or?
Yeah, I think we're seeing lots of developments also for this in doing data assimilation with machine learning models. There's a whole set of sort of quite recent papers on this, in using, for example, diffusion models to do the data assimilation process. both kind of in a bit more classical ways, but where you replace the physics-based model with, because data simulation and this analysis still involves a forecasting model, right? So you can plug in a machine learning model there, but then there's also other ways, kind of completely new ways to do data simulation that is sort of enabled by the use of machine learning techniques. I think there's also a bit of a matter of time before we see that kind of working as well as, or if it's not even, I mean, I can probably be argued that some of these approaches show that it already works as well as the traditional data simulation pipelines.
Very good. Thank you. You're muted, Olaf.
Right, thank you. So we have a question in the chat from Gideon, who asks, how long back in time was your data used to train the model? He missed that part.
So the MEPS data for the local model is just it's a year of forecasts or a bit more. Well, yeah, the full data set is almost 2 years, I think. And that's from 2021. Also they centered around, so it's just a few years back in that sense. The global models, where there are 5, our models are trained from data from 1959 to pretty much 2020. Yeah, so that's many years of data, but that's reanalysis data then. But I'd say that's a bit of an exception. Most people only use data from 79 and onwards from era 5. So yeah, a number of years less, but still quite a lot.
Great. So thank you very much, Joel, for this amazing presentation. I really enjoyed hearing about your work and the field. So I think we're good to wrap up things and see you all in 2